This lesson is an introduction to the definite integral. We'll start with a theorem that basically continues what we were looking at in the previous lesson, that if you have a continuous function, and we're not going to worry too much about that, but just a nice smooth function that you can draw without picking up your pen, and if that function is positive for all x values between some number a and some number b, then we're going to say that this symbol, the integral from a to b, that we see right here, is equal to the area under the graph of f of x from x equals a to x equals b. So what are we talking about here? If you have some function f which is positive, then one way to define the definite integral, you could say the integral from a to b of a function f of x times dx, and that's a technical piece, and we'll talk a little bit more about why that's there, but we won't focus on that right now. That we can think of this integral as simply the area you would get if you computed that shaded area under the curve f of x above the x-axis between the line x equals a and the line x equals b. Okay, we're going to continue with a number of examples and get our feet wet with this. So here's a graph of f of t, and I want you to estimate the integral from 0 to 1 of f of t dt by interpreting in terms of an area. So right away we say, okay, if we believe the definition, the integral from 0 to 1, and the definition had x's, but we're using t's here, of f of t dt, we can think about that like the area under the graph of f of t from, and now we've got t equals 0 to t equal 1. So on the picture, we know that t equals 0 is right here, t equals 1 is right here. So we're interested in computing or estimating the area under the blue graph between t equals 0 and t equals 1. Now, in this particular instance, I haven't told you exactly what the function is. You only have a picture, and all you can do to estimate the integral is to estimate that area. And there are a lot of ways to think about this. We can use the rectangle method from the previous unit, or we could just do a quick and dirty estimate and say, all right, this integral is approximately, how about this? We could chop this up into two pieces. This part is simply a square, a 1 by 1 square. And then if you think about that triangle with the dotted line, that's half of a 1 by 1 square, and our part is a little less. So instead of saying half, maybe we'll say a third. So approximately 1 1/3, or approximately 1.33. You could also do right and left-hand sums if you wanted to estimate this integral. But this is a very quick and dirty estimate for that definite integral. Okay, you can also estimate definite integrals if you only have a table of data and you don't have a graph. So let's think about the function f of t, and that's given by the following table. When t is 20, f of t is 5, and so on. So let's do a few things. Let's estimate the integral from 20 to 30 of f of t dt. Okay, so we can think a little bit about this in terms of the graph. When t is 20, we know the value of the function is about 5 from the table. When t is 22, the function value is about 7. When t is 24, about 11. When t is 26, 18. 29, and 45. We don't know anything else about how the function behaves in between those points, so again, this is really going to be an estimate. So in this situation, it's great to use the rectangles. So let's first think about trying to estimate this using a right-hand sum. So that means for the time between t equal 20 and t equal 22, we want to go up on the right-hand side and make a rectangle. And if you think about how tall that rectangle is, we went up to the dot there at 22. The f of t, the height was 7. So that first rectangle will have a height of 7, and it will have a base of 2 because we're going 20, 22, 24, 26, 28, all the way up to 30. So that first rectangle, I'll just say rectangle 1, has a height, which is f of 7, times a base, which was 2, sorry, f of 22, times a base, which was 2, and that gives us 7 times 2, or 14. The second rectangle, rectangle 2, if we use a right-hand sum, we go up on the right-hand side, and the height of that rectangle is f of 24. The base again is 2, so that's 11 times 2, or 22. The third rectangle, the height would be f of 26 times a base of 2. The picture there is 18 times 2, which is 36. And we've got 2 more to do. Rectangle 4, f of 28 times 2, which is 29 times 2, which is 58. And rectangle 5, f of 30 times 2. So that should tell us that the definite integral of f of t dt should be approximately equal to the sum of all these. So the sum of all these, if you compute that, is 220. Okay, so the second part of the question asks you to estimate the same integral using a left-hand sum. So instead of using all the right-hand endpoints for the rectangles, we would instead use the smaller left-hand endpoints. So the rectangles that I'm shading in here. What you'll notice is that doesn't change much. So if I think about the left-hand sum, we know that the base of all of the rectangles is 2 units because the t values that we were using were 2 units apart. And then we know the height of the first rectangle is 5. The height of the next rectangle is 7. The height of the next one is 11. The fourth one is 18. And in fact, the last, or the fifth rectangle, has height 29. We never actually use this last piece because we're really looking at the left-hand side and we're looking at the height of the function at t equals 28. So if you just do the shortcut instead of doing computing the area of each rectangle individually, this isn't too hard to figure out pretty quickly that the estimate for the left-hand sum would be 140. These are pretty different estimates. This isn't a large number of rectangles, but one of the ways we can think about getting a better estimate is look at the function and ask ourselves if we were overestimating or underestimating. And if you think about the way the function was increasing from left to right, when we computed the right-hand sum, we were always overestimating. If perhaps the function was behaving something like this, we always had extra area. Similarly, the left-hand sum we were always underestimating. So one of the things that you can do when you have a left-hand sum and a right-hand sum, one of which is an over and one of which is an underestimate, you can just take the average of both of those. So if I want to use both estimates to make the best possible estimate, I could just say, let's average these. So average the left-hand sum and the right-hand sum. And that's going to give me 220 plus 140 over 2. That should be 360 over 2, or 180. Okay. So let's look at another example, estimating another definite integral from a graph. So in this situation, we've got t measured in seconds, and we've got velocity measured in feet per second. And I'm asking you to estimate the integral from 0 to 6 of f of t dt by interpreting it in terms of an area. So if we look at this, the integral from 0 to 6, sorry, this is f of t dt. And that means we're looking for the area under the curve from time 0 to time 6, and it looks like this area right here. And now we're kind of in good shape because we don't have to do a whole bunch of rectangles because these are some pretty nice, this is a pretty nice area, and I'm going to suggest the following method. If you look at this, it looks like the function is horizontal for this bit. And if you follow that down, that looks like it's at about t equal 2. And so if we could compute that area, that's pretty easy. That's just a rectangle. And that rectangle has a base of 2 and a height of 15. And if you want to think about units, again, 2 is in time, seconds, and the 15 is in feet per second, so you would get total feet for that. And then if you look at the triangle right here, we can use the area of a triangle formula. So 1/2, the base there, the base is between time 2 and 6, so base of 4. And again, the height of that triangle is 15. So that equals 30 plus 30, and it looks like 60. And if you think about the units, feet per second times seconds, that should be feet, because this was essentially a velocity problem, so we're getting a distance. So we can also think about the fact that this definite integral told us the distance we traveled in the first 6 seconds. Okay, so let's look at another example using the same graph, and in this case we're going to look at trying to estimate the integral from 0 to 18 of f of t dt by interpreting terms of area. And so there's something you need to know that's important, and I'm going to write it down here, that if the function is negative, and you want to think of that like below the x, or in this case the t-axis, then the area between the function and the axis contributes negatively to the integral. And there's a couple things that I'll say about this. It's tempting to say that the area is negative, and that doesn't make sense because area is a positive quantity. But if we're looking to estimate the integral from 0 to 18, in this case of f of t dt, you can think about 3 big regions. There's kind of region 1 here, the area between the function and, in this case, the t-axis. There's region 2 there, the area that goes from t equals 6 to t equals 16. Between the function and the axis, that's below essentially the t-axis here. So this is t and this is f of t. And then we've got this region 3 right here. And so essentially you want to think about this as the area of region 1 minus the area of region 2, that stuff that shows up below the axis, plus again the area of region 3. So in this case, we just need to estimate the areas of those 3 regions. And we've done a little bit of this before. So if I'm looking at region 1, we can think of this as a rectangle. It's 2 by 15. So for area 1 of region 1, we get a 2 times 15, we get 30. We get also then the area of this triangle. Area of a triangle is 1/2 base times height. So 1/2 times 4 times 15 is again 30. That's region 1. For region 2, we can think of a rectangle and 2 triangles. Again, this triangle has base 4 and height, in some sense, it's inverted, 15. So I believe that's an area of 30. This
rectangle right here. Again, base 4, height 15, so that's 60. And then this little piece, this triangle piece right here, that's got base 2 and height 15. So that looks like it's going to be a 15. And then we just need to add in this last little bit, and I believe that's a 15 also. So if we compute this, I think these 15s go away, one of these 30s cancels, and it looks like we get negative 30. And if you think about the units, velocity was feet per second. Time was in seconds. So the area under the curve should be feet per second times seconds, or feet. And that's essentially the total displacement at time 8, from time 0 to time 18. And let me say a little bit about displacement versus distance. What we're not computing when we have functions with negative velocity, we're not computing distance traveled. And the thing you want to think about here is, say you start at some start time at t equals 0. That's your start. And you're traveling in the positive direction for a while, and you cover some distance. And that's essentially what region 1 is talking about. And then you turn negative velocity, which means you go backwards. So right here in our picture at time 6, we started at negative velocity. That means we turned around and went the other way for a while. And then at time 16, we started to come back. So at time 18, the idea was, what was our total displacement? What was the distance from where we started to where we wound up? And that was 30 feet in the negative direction, or essentially to the left here.
So the last thing we're going to talk about in this unit is the area between curves. And this is a pretty simple idea. We probably won't belabor this too much. But if you've got two functions and you know that one of them, g of x, is less than the other, f of x, between 2 points that you're interested in, a and b, so we'll say b is there and a is there, then if you wanted to know the area between curves, and this will come in handy with different applications, it kind of is intuitive. You want to think about the area underneath the red curve minus the area underneath the blue curve, but that's just a definite integral of the top function minus the bottom function. So that's a definition, and we can try an example at a later date. So what I'd like you to do is reflect and ask yourself if you can interpret definite integral as an area, use the right-hand sums and left-hand sums to do some estimates of definite integrals. You definitely want to be able to estimate integrals with right and left-hand sums and from tables of data using right and left-hand sums. And then could you quickly find the area between two curves?